now that we know a little bit about key features, we are going to look at our 9 parent functions and describe their characteristics. So a linear parent function, that is when f of x is equal to x. So typically you're used to seeing that as just that straight line with a slope of 1. But if you ever thought about how do you actually graph that, you could make an xy table. And because f of x is equal to x, all of your inputs are going to be equivalent to your outputs. So you could graph those points and then connect the dots. So if you're ever unsure what the graph looks like, make a table. So this graph we just drew has a domain of all real numbers. I'm going to put it in both notations. It also has a range of all real numbers. We cross through the origin, so that is going to be our x-intercept and our y-intercept. The maximum number of roots or zeros, that means how many times could it cross the x-axis? That is just 1 time. And then end behavior, so as x is going off to positive infinity and negative infinity, what's happening to my y values? Well, as x is increasing positively, so is y. And as x is increasing negatively, y is also doing the same thing. And then my graph is continuous because I can draw it without ever having to pick up my pencil. And then one more thing I want to add in, since we talked about it on our key features, is does this graph have an axis of symmetry, or is it symmetrical? And the answer is no, it is not symmetric. There's nowhere I can fold it in half and all my matching pieces will line up. Okay, on to the next one. I've got absolute value. This is where f of x is equal to. The goalpost is your symbol for absolute value. And what this tells us is how far away we are from 0 on a number line, which means it's always positive because we always measure distance in positive values. So like the number 1 is 1 away from 0, 2 is 2 away, -1 is also 1 away, -2 is 2 away, and so on. You could plot more points if you really wanted. And 0 is 0 away. So the key thing here is that your graph looks like a big V. So the domain of this graph is also all real numbers. But for my range, my y values, I start at 0 and then go off to positive infinity. So that is going to be that y is greater than or equal to 0, or bracket 0 to positive infinity. We're also at the origin again, so my x and y intercepts are both going to be 0. And then the number of times that this could possibly cross the x-axis is twice. So if I shifted this down or flipped it upside down, if you think about that yellow graph we did together in the last video, that one crossed it twice. So the maximum number of times it's going to cross is twice. And then our end behavior, again, as x goes off to positive and negative infinity, what happens to my y's? As x is increasing positively, y is also getting bigger positively. And as x is increasing negatively, y is still increasing in the positive. And we also, again, have a continuous graph. And this one does have an axis of symmetry at its vertex. So this one is symmetric or symmetrical. Okay, quadratic. This is where f of x equals x squared. So if you wanted to make a table with a couple x values to put in, we know that 1 squared is 1, 2 squared is 4, -1 squared is going to be positive 1 because of a negative times a negative, and -2 squared is positive 4. So those are the ones that are going to fit on this graph. There are more. And then, of course, we are still at the origin. And this one looks more like a U, and we call this shape a parabola. So we still have a domain of all real numbers here. And our range starts at 0 and goes up to positive infinity. So y is greater than or equal to 0, or bracket 0, positive infinity. Again, we're at the origin, so that x-intercept and y-intercept are both at 0, 0. Similar to the absolute value, the maximum number of roots I'm ever going to have is 2. Whether that's shifting it down or flipping it upside down, it will only ever cross the x-axis twice. And then our end behavior is also going to look very similar to that absolute value. As x is increasing positively, y is also increasing positively. As x is increasing negatively, y is still increasing in the positive. This is also continuous. I can draw it without picking up my pencil. And we do have an axis of symmetry here along the vertex, so this is a symmetrical graph. Okay, 3 down, 6 to go. On to cubic. This is where f of x is equal to x to the third power. So, putting a couple values into our table so we can graph them. 1 to the third power is positive 1, but negative 1 to the third power is negative 1. If you think about this, I've got a negative times a negative times a negative. When we had 2 negatives, that became positive, but that third negative makes it negative again. So when you have odd powers, your negative inputs will have negative outputs. 2 to the third power is 8. Remember, that's 2 times 2 times 2, not 2 times 3. And negative 2 will be negative 8. So those 8s are going to be a little bit off the graph, but just to get an idea of the shape, I'm going to do my best to plot them where they might be. And so this is kind of the curviness that our graph has for cubic. It's kind of like I took my parabola from up above and my left side flipped upside down, like one of my arms got lazy. So this has a domain of all real numbers. We also have a range of all real numbers. We are at the origin again, so those x and y intercepts are both at 0, 0. The maximum number of times that this one is going to cross your x-axis is once. And then our end behavior, as x goes off to positive infinity, y is also going off to positive infinity. As x goes off to negative infinity, y is also going off to negative infinity. It is continuous, and we do not have an axis of symmetry here, so it's not symmetric. Okay, we just have 5 more to talk about. The next one is our square root parent function. Now, with square roots, we cannot take the square root of negative numbers. So all of our inputs for what we're graphing are going to have to be positive. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. And you could continue doing all of your perfect squares to get clear, pretty points to graph, but we're only going to be able to actually fit 3 of these on here. And my graph kind of looks like half of a parabola. So that domain, again, because I can't take square roots of negatives, my x values have to stay greater than or equal to 0, or bracket to positive infinity. And for that same reason, my range is also going to have to remain positive, so greater than or equal to 0, or bracket 0, positive infinity. We do cross through the origin, so we have that x and y intercept both at 0, 0. This one also is going to have a maximum number of roots of 2, depending on where you shift it around. It could cross the x-axis twice. Oh, forgive me, I'm sorry, just once. End behavior, as x goes off to positive infinity, x is also going off to positive infinity. Now, all of our other graphs, we were going off to negative infinity for the second one, but x does not go to negative infinity. So the other end behavior of my graph is as x approaches 0, the y value is also approaching 0 here. And it is continuous, and I don't have an axis of symmetry, so it is not symmetric. Okay, cube root is the third root, so like a radical but with a 3 over it. So it's the cube root, so backwards of our cube function. But we could have negatives with our cubes, so we can also take cube roots of negative values. So like 0 is obviously 0, 1 is 1, negative 1 is negative 1, and then thinking backwards from our other one, the cube root of 8 is positive 2, and the cube root of negative 8 is negative 2. So that gives me a good amount of values to plot here. So it's going to look similar to the cube root one, but instead of going up so high, it's going to go out horizontally a little bit further. So there is our cube root function. This has a domain of all real numbers, also a range of all real numbers. We pass through the origin, so we've got a 0, 0, x and y intercept. We can only cross the x-axis once here. As x goes to positive infinity, y is also going to positive infinity. And as x goes to negative infinity, y is also going to negative infinity. We are continuous, but we are not symmetrical here either. Okay, 3 to go. Reciprocal, which you can also call rational. That is where f of x is equal to 1 over x. So we're going to have two parts to this graph because I cannot divide by 0, which means x cannot be 0. So I'm going to have to find values that are greater than 0 and values that are less than 0 to get an idea of what this graph looks like. So I'm going to do some positive ones first, like 1. 1 divided by 1 is 1. Or for 2, 1 divided by 2 is 2. So 1/2. And it's going to continue shrinking. So this is an example of a graph that is going to have some asymptotes. But there are my positive values. And then for some negatives, like -1 divided by 1 is -1. 1 divided by -2 is -1/2. And I could even go on to -3 with -1/3. But it's going to continue getting closer to that axis here without crossing. Same with my y's. So our domain and range look very different here. We are having to eliminate one of my values. Neither of them can be 0. X cannot be 0 and y cannot be 0. And then neither of these are crossing the x and y axis, so I do not have an x-intercept or a y-intercept. I could, if I shifted this around a little bit, I could have up to 2 roots. And then our end behavior is going to be a little bit different here as well. As x is going off to positive infinity, y is approaching 0. And as x is approaching negative infinity, y is also approaching 0 again, but from the bottom. We could also talk about the end behavior as it approaches 0, but it's going to be different depending if you're coming from the left and the right, so we won't confuse you about that today. It is continuous, and then you can see right here we have asymptotes. So we have a vertical asymptote where x is equal to 0, and we have a horizontal asymptote here at y equals 0. We have 2, and this is another non-symmetrical graph. Okay, home stretch, we're in the final 2. Exponential, this is when f of x is equal to something where x is in your exponent. So it could be the number 2, 3, a fraction, anything but 1. But I'm just going to do it with 2 to the x because that's going to be pretty simple to graph here. So if I start with like 0, anything to the 0 power is 1. 1 would be 2 to the first power, which is 2. 2 would be 2 squared, which is 4, and so on. So I can graph more of those high values. But what happens when I have negative values? If you recall, a negative exponent, like if I have 2 to the -1, that's like moving it to the denominator, 2 to the 1 or 1/2. Similarly with -2, that would be like -1 over 2 squared, which is 1/4. So on the left side of your graph, you're going to be getting fractions, but it's never going to cross and become 0 or become negative. So we have another asymptote there. So our domain is all real numbers, but my range, and I forgot to write the other half of that, my range is just that y has to be greater than 0. It's never going to be equal to 0, and it's never going to be negative. I do not have an x-intercept, but we do cross the y-intercept here at 0, 1. If I were to shift this up or down, I could potentially have 1 root. And then end behavior as x goes to positive infinity, so is y. And as x goes to negative infinity, y is approaching 0. It is continuous, and we have a horizontal asymptote here at y equals 0. And this is a non-symmetrical graph. And I'm going to run out of time for the last one, but stay tuned for logarithmic, our very last parent function. That is when you take the log of a value. So hold tight.